Welcome to Chapter 9, Correlation, Regression, and Stratified Analysis. This video content is based on Essentials of Biostatistics in Public Health by Lisa M. Sullivan. In public health, we don't just describe relationships, we analyze and explain them. This chapter explores how we account for confounding, test for effect modification, and use regression techniques to model complex data. First is confounding and effect modification. Confounding occurs when a third variable distorts the true relationship between an exposure and an outcome. A confounder must be associated with both the exposure and the outcome, but not lie on the causal pathway. For example, if we're studying the link between exercise and heart disease, age might confound the relationship because it's related to both. To deal with confounding, we can use stratification, matching, or multivariable regression. Effect modification, also called interaction, occurs when the relationship between exposure and outcome differs by levels of a third variable. Unlike confounding, effect modification is a real difference, not a distortion. Stratified analysis helps us identify whether we are seeing confounding or effect modification. Second is the Cochran, Mantel, Haenszel method. The CMH method helps us control for confounding across multiple 2x2 tables. We stratify the data based on the confounder, calculate stratum-specific odds ratios, and then combine them. This method assumes no effect modification across strata. For each stratum, calculate the odds ratio. Then sum the stratum-specific numerators and denominators using the CMH formula to get an adjusted odds ratio. This gives us a more accurate estimate of association, accounting for confounding. Third is Introduction to Correlation and Regression. Correlation measures how strongly two continuous variables are linearly related. The correlation coefficient R ranges from 1 to +1. R0 means no correlation. R means positive association. R0 means negative association. Linear regression models the relationship between a dependent and one independent variable. The equation is y equals a plus b times x, where a is the intercept and b is the slope, the change in y for every unit increase in x. Regression lets us predict the outcome and quantify the effect of a predictor. Fourth is multiple linear regression. Multiple linear regression includes more than one independent variable. This allows us to control for confounders and estimate independent associations. The equation is y equals a plus b1 times x1 plus b2 times x2 and so on. Each coefficient represents the effect of that variable while holding other variables constant. We assess the model fit using R-squared, which tells us how much of the outcome variation is explained by the model. We also check for assumptions, linearity, normality, constant variance, and independence of errors. Fifth is multiple logistic regression. When the outcome is dichotomous, like disease versus no disease, we use logistic regression. Equation, the log of the odds of the outcome equals a plus b1 times x1 on bt times x2 and so on. This gives us the log odds, which we exponentiate to get odds ratios. Multiple logistic regression lets us adjust for confounders, predict the probability of an outcome, estimate independent effects. It is a powerful tool in both clinical and public health research. This chapter brought together several important tools. We covered confounding and effect modification, the Cochran Mantel Haenszel method for stratified odds ratios, correlation to describe relationships, linear regression to predict continuous outcomes, logistic regression to analyze binary outcomes and adjust for confounding. These tools help us understand, quantify, and control complex relationships in public health data. This concludes Chapter 9, Correlation, Regression, and Stratified Analysis. Next, we move into more advanced regression techniques. This video content is based on Essentials of Biostatistics in Public Health by Lisa M. Sullivan.